Good day everyone, and welcome to our course on hydraulics. In this first module, we will build the foundational understanding needed to grasp the behavior of fluids and the principles that govern hydraulic systems. Hydraulic engineering is a branch of civil engineering that deals with the flow and conveyance of fluids, primarily water and sewage. But it also overlaps with mechanical engineering in areas where pressurized fluid systems are involved, such as in hydraulic machinery. Think about dams, canals, irrigation systems, water supply networks, stormwater drains, turbines, and pumps. All of these rely on the understanding and application of hydraulic principles. The goal of hydraulics is not just to understand how fluids behave, but to control and use them efficiently. This includes designing systems that minimize losses, predicting flow behavior under different conditions, and ensuring safety and stability in both natural and artificial systems. Hydraulics is deeply rooted in fluid mechanics, which is the branch of physics that studies fluids at rest and in motion. We can't design a spillway, measure the discharge of a river, or size a water pipeline without applying fluid mechanics principles. Before we get into the mathematics and equations, let's start with the most fundamental part, understanding what fluids are and what makes them unique. 2. Description and properties of fluids. A fluid is any substance that can flow and take the shape of its container. Both liquids and gases are fluids. Unlike solids, fluids cannot resist shear stress without deforming. The most important properties of fluids that we will consider in hydraulics include density, ρ. This is the mass per unit volume of the fluid. In SI units, it is measured in kilograms per cubic meter, kg/m superscript 3. Water at 4 degrees Celsius has a density of about 1000 kilograms per cubic meter. Specific weight, gamma. This is the weight per unit volume of the fluid, usually expressed in newtons per cubic meter, n/m superscript 3. Specific gravity, Sg. This is the ratio of the density of a fluid to the density of water at a standard reference temperature. Viscosity, μ. This is a measure of a fluid's resistance to flow. A thick fluid like honey has high viscosity, water has low viscosity. Viscosity affects energy losses in pipelines and open channels. Surface tension. This is the property of a liquid surface that causes it to behave like a stretched elastic sheet, important in small-scale fluid interactions. Compressibility. Liquids are generally considered incompressible in hydraulics, whereas gases are compressible. Knowing these properties allows engineers to predict how fluids will behave under different conditions, whether in motion or at rest. 3. Hydrostatics. Pressure variation in fluids. Hydrostatics is the study of fluids at rest. The most basic principle is that pressure in a fluid increases with depth due to the weight of the fluid above. If we take a container filled with water, the pressure at a certain depth depends on the fluid density, ρ, the acceleration due to gravity, g, the depth below the free surface, h. So the deeper you go underwater, the greater the pressure. This principle is critical for designing dams, submarines, and deep-sea structures. In hydrostatics, we also study the forces on submerged surfaces, both plane, like the face of a dam, and curved, like the inside of a pipe bend. Calculating these forces correctly ensures structural stability. 4. Buoyancy and stability of floating bodies. Another key topic in hydrostatics is buoyancy, the upward force exerted by a fluid on an immersed body. This is described by Archimedes' principle. A body wholly or partially submerged in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the body. This principle explains why ships float and why submarines can submerge and resurface. When it comes to floating bodies, stability is a critical factor. Even if an object floats, it must also resist overturning. We evaluate this using concepts like meticentric height, which indicates how stable a floating vessel will be when tilted. 5. Laws of inviscid flow. An inviscid flow is one where viscosity is neglected. This is an idealization. Real fluids always have viscosity, but in many cases, especially at high Reynolds numbers, viscous effects are small enough to ignore in large-scale motion. 2 important laws govern inviscid flows. Euler's equation describes the relationship between pressure, velocity, and elevation in a non-viscous flow. Bernoulli's equation, a special case of Euler's equation, which states that for steady, incompressible, inviscid flow along a streamline, the total energy, pressure energy plus kinetic energy plus potential energy, remains constant. Bernoulli's equation is fundamental in hydraulics. It explains why airplane wings lift, why pressure drops in a constricted pipe, and how venturi meters work. 6. Continuity equation. The continuity equation is based on the conservation of mass. For incompressible flow, it simply states that the volume flow rate entering a control volume must equal the volume flow rate leaving it. If we have a pipe that narrows, the velocity of the fluid must increase in the smaller section to maintain the same flow rate. This is why nozzles and orifices increase fluid speed. 7. Energy equation, Bernoulli's principle. As I mentioned earlier, Bernoulli's principle is central to hydraulics. In energy terms, the total head, or total energy per unit weight of fluid, is made up of pressure head, velocity head, elevation head. The principle allows us to relate conditions at one point in a flow to conditions at another, assuming negligible friction losses. 8. Momentum equation and applications. The momentum equation is derived from Newton's second law, applied to a fluid system. It relates the sum of forces acting on a control volume to the rate of change of momentum of the fluid. Applications include calculating forces on pipe bends, jet impingement on surfaces, thrust in turbines and pumps. 9. Dimensional analysis and model theory. Hydraulics often requires predicting the performance of large systems based on small-scale models. Dimensional analysis helps identify the dimensionless groups that govern the behavior of the system, such as the Reynolds number, Froude number, and Mach number. Model theory then uses these dimensionless parameters to ensure that model tests can accurately represent the prototype system. That concludes Module 1, where we've established the basic language and laws of fluid mechanics, covering fluid properties, hydrostatics, buoyancy, inviscid flow laws, continuity, energy, momentum, and dimensional analysis. In Module 2, we will apply these principles to real-world hydraulic problems, covering flow in pipes and open channels, energy losses, flow measurement, hydraulic jumps, and the design of hydraulic structures.